Hello, I'm John Coleman Hanson, and this is Lab 4 for Physics 2211. For the introduction for this lab, first the purpose. We had to examine the motion of a spring mass system by using tracker. Then had to use glow script to produce a model of its motion based on experimental data. Preview of results. The period of oscillation for the x direction was 1.524 seconds, and in the y direction it's 1.429 seconds. Models, principles, and figures. Here are some formulas that were used: the energy principle, the momentum principle, and Newton's second law. For an experiment, the system was the mass spring and Earth. The surroundings was everything else. And some of these conditions were found in pre-lecture video 52. The mass, 0.402 kilograms. The position of mass, which is found by setting up a coordinate system and tracker. The length of spring was given, and the time between images of movie was given. As you can see here in tracker, that the fixed position is where the coordinate axis origin sits on. Then you can see to the right that there is an oscillating motion. This is because of the spring, and you can see all the centers of masses that were tracked, and they were plotted in the x and y direction with time. Calculations. First, to find the average oscillation, which was represented by the variable t, is just add in the x and y direction, and it's 1.48 seconds. Then, using these two formulas, you can find k, which was the spring constant, 7.25. Then you're able to find L naught, which is the magnitude of Fg equals the magnitude of the force of the spring. And you're able to plug in some other things that we know, and I got 0.08. The code for this project for the model, to the left, you can see the spring constant is put in and the relaxed length of the spring. Then the next three lines, you can find L, and then L hat, and then you're able to find S, and we just know S is the magnitude of L minus the relaxed length of the spring, and we know this from previous formulas during this course. And the next four lines, they just deal with simple formulas, but making sure that the variables are represented correctly, using kinetic energy, gravitational potential energy, spring potential energy, and total energy. Then to the right, there's the while loop, the force of gravity using the vector and the ball dot m variable. Then the force of the spring using L hat and S, and then the spring constant in negative direction. Then using object's velocity update formula and the object's position update formula. Then you had to update the spring. And then towards the bottom, you had to plug in formulas again, just using the correct variable names and plugging in what we know. On the slide, you can see the experiment versus the model for the x and y direction. To the left, we have the x direction, and you can see that the model and experiment match pretty well. To the right, the model and experiment are a little off. The model has a higher y direction. So what does it mean? We're talking about this in the sense for change in energy versus time in this graph and looking at it. And you can see, and from this graph, you can answer the question, does the energy principle apply in this case? And yes, it does, because the change in energy of the system remains constant and no surroundings that influence the system. So the periods of oscillation, it's estimated from tracker, going from the peaks, and I got 1.524 seconds, as I mentioned earlier, in the x direction, and 1.429 seconds in the y direction. Periods of oscillation are not the same. Conclusion from this is they're not traveling in a circle. Conclusion of the lab, possible sources of error, tracker not accurate due to center of mass being off when you're tracking it. Also, not correct numbers could have happened for calculations for T and K and the relaxed length of the spring. And there could also have been some rounding errors. That is all for this lab. Thank you.